Lab 4, Oscillations, by Justin Siegel. The purpose of this lab is to observe and measure the motion of a mass swinging in an arc while oscillating on a spring. Using these observations, we have to create a model that follows the motion and measures the energy changes as well. For the results, I found that potential and kinetic energies were always in opposite trends, so the total energies always equaled 0. First, I inputted the video given to us into Tracker. We were given that the length of the spring is 0.7 meters and that the origin should be placed at the fixed attachment point so that the direction of the spring is in the negative y direction. I then started to calculate the center of the mass when the man first released it from his hand at frame 5. I kept calculating it for 3 full oscillations. The x movement of the mass first time was plotted up here on the top right, as well as time, the x position, and the y position below. After importing the starter code into GlowScript, I first changed the ball's mass to 0.402 kilograms, as that was given to us. I then changed the ball's position to the vector -0.125, -0.6240, as that is the position of the mass at time 0 in Tracker, and the velocity was 0 initially. We then changed the spring constant to 6.83 and L naught, or the relaxed length of the spring, to 0.123, as those were found in our edX videos. We then changed the length of the string to the ball's position minus the string's position, L hat to L divided by the magnitude of L, and S to the magnitude of L minus L naught. We then updated all the formulas for all the energies so that we could find the kinetic energy, the gravitational potential energy, the spring potential energy, and the total energy, which is the addition of all 3 of these energies. Finally, I had to alter the while loop to make it while t is less than 4.9 seconds, as that was the longest time on my tracker. I updated the F grav vector, the equation for F spring, and the F net total equation. I then had to update the position and velocity update formulas, as you can see here. Later, I re-updated the spring. And finally, I had to calculate the energy changes to where delta K is K minus K initial, delta UG is UG minus UG initial, delta US is US minus US initial, and delta E is E minus E initial. Next, I copied all of the X and Y positions for the mass from Tracker into an Excel sheet and made it into a CSV file so that it could be run and compatible with our GlowScript program. I then ran my GlowScript program by importing the CSV file we created earlier. As you can see, the ball oscillates in a circular motion, but in a different circular motion each time. The change in energy versus time graph shows all the components of energy, delta K, delta U grav, delta U spring, and delta E over each oscillation. The first question, is the energy principle upheld, is actually answered by this graph. And the answer is yes, because delta E stays constant at 0 the entire time. Energy is not gained nor lost. Next, in the X position versus time graph, you can see that our observed X position is not exactly the same as what it was supposed to be in this model. That is either due to my error, because I did not track the center of the mass correctly, or due to the error of the man who originally did the video. Finally, we have our Y position versus time graph, and same thing applies. This was due to my error or due to his error, as it is not perfectly lined up. After observing my data, I found the gravitational force to be the vector 0, -3.94, 0 newtons. The spring force, but first we had to find the spring constant. So using the equation, T equals 2 pi times root m divided by k. Rearranging it a little bit, it became 4 pi squared times m divided by t squared. So overall, k ended up equaling 6.67 newtons per meter. And I found that T to be 1.66 by finding the difference between the first oscillation and the second oscillation, and then the second oscillation and the third, then finding the average of those two oscillations. And then overall, the force of gravity equals the force of the spring, so the initial, or L naught, is 0.109 meters. For the second question, comparing the oscillation period in the x direction and the y direction, I first found the initial positions with their initial times. I then noted when the positions were almost exactly the same and noted those down along with their respective times. As you can see, the average for the times of the x direction is 1.61, while the average for the y is 1.52. These are not exactly the same due to the error that could have possibly been my marking of the center of the mass, or the man who made the video who could have been shaking, or any other possible error. Thank you so much for watching my lab.